Hey, today we're going to look at graphing rational functions. And if you did the INB, not the INB, the Delta Math, the last one that I know was having a little bit of problems the other day or last week when I assigned it, but it's the one where you have to find the y-intercept and put the graph on it. If you can do those, then this should be pretty easy, but it's going to just be more in depth. So this IMB, I'm just going to go just like we did the other one. I'm going to go through and just explain what we're doing on this IMB, and then on the next one, we will do an example. So I'll kind of go back and forth on these, and hopefully that will make sense. So the very first thing that you want to do is you're going to want to factor um, the rational function. So step one is up here, we're going to factor. So, and sometimes the numerator and denominator are not factorable, but that's what we're going to do. And so when you factor, you're going to do the domain. And remember, the domain are the zeros of the denominator. And we would write that in interval notation. Once we find the zeros of the denominator, we're going to write those as values that it can't be here, right? X can't equal um, the domain restrictions. Okay, and then once we do that, we're going to identify them if they're vertical asymptotes. So factors of the denominator that don't cancel with denominator. Okay, and then the wholes are the factors that reduce with the, I spelled denominator wrong up here. Okay, so I'm going to go over and I'm going to do that on sample problem number one. Okay, so here's sample problem number one. The first thing that I want to do is I want to factor. So this gets me x minus 7 times x plus 2. And I know that this is a difference of squares. And I end up with this as my factored form. And so now I'm going to use my factored form, and I'm going to go to the denominator and notice that I have 2 zeros in the denominator. And so x can't equal -2 or 2. So here's my denominator, and my discontinuities are x can't equal -2 and 2. Now, of those discontinuities, one of them is going to be a vertical asymptote, or both of them are going to be vertical asymptotes, and one of them is going to be a whole, or both of them are going to be a whole. So I have to go back up to my factored form, and I'm going to reduce. So this is where I want to reduce the factored form. Okay. If it's reducible, then what you know is that factor is a whole. So notice when I reduce this, I get x minus 7 on top and x minus 2 on the denominator. So because it reduces, I know that x equals -2, that is the zero of the factor x plus 2, is a whole because it reduces out. And then the vertical asymptote is the one that didn't reduce out the 0 in the denominator that didn't, which is the 0, 2, positive 2, when you take the factor and solve it for 0. Okay, so this one I have both a whole and I also have a vertical asymptote. Once I have my vertical asymptote, I'm done. When I have a whole, I'm not done because a whole is a point on the graph that's broken. So I need to find the point. Right now, I know the point occurs when x is -2. So to find the y, I'm going to need to plug it back into my function. Well, obviously, if I plug it into the original factored form, it's going to cause me to have a 0 in the denominator, and that doesn't give me a number. So when we plug it in, we need to plug it into the reduced form. Since that whole reduces out, when I look at the reduced form, now the -2 is not a 0 of the denominator because it's reduced out of that. So I'm going to plug in -2 in for x, and I'm going to find where that y is. So I'll plug in -2, and I get -9 over -4, which is 9/4. And that is the location of my hole. Okay, so now we've done everything that we stated before, and I'm going to go back to the fill-in. Okay, on the fill-in, we're right here. You might want to factors that the factors that reduce with the denominator, and then you could plug back into reduce to find y coordinate. Okay. So the next thing I want to do is find my x-intercepts and my y-intercepts. So remember, if I have a fraction, so I have some p of x over q of x, this is zeros, make the fraction undefined. 0 is where the y is 0. Because if I get a 0 in the numerator, then my function outputs a 0. If I get a 0 in the denominator, that's where my function outputs a undefined or broken part of my graph or my number system. My y-intercept is just where what? Where my x is equal to 0. So I'm just going to set x equal to 0. So we're going to do those two things on sample number 1. Okay, so up here, we're going to always go to the reduced form because obviously x plus 2 was a 0 of my numerator. However, it's really a whole, so I can't call it an x-intercept. So this is the reduced form. And I'm going to take my numerator and I'm going to set it equal to 0, and that's my x-intercept. So it's at x equals 7. Notice if I plug 7 back into that numerator, I get 7 minus 7, which is 0. And in the denominator, I would have 5. So 0 divided by 5 is 0. So when x is 7, my y is 0. Okay. For the y-intercept, similarly, I'm going to do the same thing. I'm going to go to my reduced function, and I'm going to plug in 0 for x. And I get f of x or y is equal to 7 halves. So when x is 0, I'm at 7 halves. That's a 7. Or it's kind of sloppy. Okay. So that's the main meat of this problem. We have a lot of stuff that we can put on our graph now, actually. We can put in a vertical asymptote at 2. I also can put in an x-intercept of 7. 1, 2, 3, 4, 5, 6, 7. I can also put in a y-intercept at 7 halves, which is 3.5. I can also put a hole in the graph, which is at -2, and then 9/4 is 2 1/4. So -2, right? And then 2 1/4. Notice how this is all kind of looking like it's matching up, my point, especially my y-intercept and my hole, okay? And so I've got everything in there that I've just done, and I'm just going to keep moving on forward, okay? So my next thing that I want to do is I want to go back to my fill-in. So test the behavior around the vertical asymptote. We're not going to do that with the holes, so you can get rid of that. So the first thing I want to do is put my my restrictions of my vertical asymptote. I'm going to put my vertical asymptote on a number line, and I'm going to choose close numbers and a close number. And I'm going to see, does this result in a positive or negative number, a positive or a negative? And what I want to know is my graph approaching the vertical asymptote on this left or on the right side over here? Is it approaching it at the top of the graph, or is it approaching at the bottom? So I'm going to test both of those sides. So I'm going to do that over here in sample number 1. So I'm going to put my vertical asymptote at 2 on there, and I'm going to pick a number to the right. Remember, really close, 0.001 and positive 1.99. And I'm going to plug that in. We really reuse the reduced form from now on. It's a lot easier. So here's my reduced form. And if I plug in 0.001, right, I get this denominator of 0.001. And then up here, I really don't care about anything except for 2.001 minus 7 is some negative number, okay? Because when I take a negative number and I divide it by 1,000ths, this is going to output something that says negative big, something negative really large, okay? Because this one's a positive and that one's a negative. So I know this is going to be going down on the right side. So if I go down to my asymptote down here, I know my graph is going down on the right side. Okay, now I'm going to do the same thing on the left side. And the left side, I'm going to plug in x minus 7 over x minus 2. If I plug in 1.999, then I'm going to get negative 0.001. So really a negative 1,000th. And if I plug in 1.99 in the top, I'm going to get some number that's negative. And this is going to get me a really large positive, because a negative divided by a negative is a positive. So some really large number. And if we don't understand that, you can go ahead and plug those numbers in your calculator and generate what number that is. It will be a really big number if you're having a hard time following that. So on the left side, since this is the left side, 1.999, I know my graph is going up, which matches perfectly with what I have going on right here. Okay. Next, we'll go back to my fill in. Okay. Next is I'm going to turn my end behavior. My end behavior is my horizontal asymptote. Okay. So the degree of the numerator is, remember, this is where it can be bigger, equal to, or less. And so if it is less, it's y equals 0. If it's equal to, it's leading coefficient divided by leading coefficient. And if it is greater, the degree of the top is greater, then what's going to happen is then you divide. And it's going to be not a non-horizontal. So it could be a slant or it could be a quadratic. It depends whatever equation you get when on the top when you divide the two polynomials. Okay, so now we're going to go back to sample 1 and we're going to compare the degrees. So these degrees are the same. And so I know it's the leading coefficients. So the leading term of both of these are x squareds, right? That's the leading term. The leading coefficient, the number that's in front, is both 1. So this comes out to y equals 1. Okay, so I'm going to plug that into my graph. Okay. And now the next thing that I want to do is look at whether this crosses the horizontal asymptote, because sometimes when I do my graph over here, it can cross this asymptote, the horizontal, and then just approach it from the top instead of the bottom. Okay, so I'm going to look, and what all we do there is we take our function, our reduced form. Reduced, if it reduces, you always use the reduced from now on. It's a lot easier, and you're going to just set it equal to that horizontal asymptote. So I'm saying, what x value must I be to equal 1? And I know if my y is 1, I'm a point somewhere on this horizontal asymptote, meaning I cross it. Okay, so what I'm going to do is I'm going to try to solve this and see, is there an x value where my y is 1? Okay, so I'm going to always multiply by the denominator. And I'm going to move my x first and realize that I get a no solution. So that means I don't cross it. There is no x value where my y is 1, meaning that my graph does not cross through the asymptote. So it's just going to approach it. And there's that hole, right? It's just going to come out the other side. And there's my graph. Okay, now I want to determine if there's symmetry, the same way we've been doing. So you're just going to plug in f of negative x. I'll plug that into the reduced, and I get negative, what is that? What was the reduced form? There it is. Negative x minus 7, and then negative x minus 2. And notice it didn't completely change signs. One term changed signs, but not both. Both of the constants, so there's no symmetry. I'm not going to look at my graph until there's no symmetry. And I've already compiled my graph as I went through, and this is what it looks like. And I'm just going to fill in the rest of this information on the fill in. And this says, what do you do to see if it crosses? Set reduced. If it's reducible, reduce function equal to the horizontal asymptote. If it's not reducible, you just use the original function. I don't want you to think, oh, it's not reducible, so I don't have to do this. So yes, but you set the reducible function, and it's reducible if it has a hole. So if it doesn't have a hole, you have to set the original function equal to it. So set reduced function or original. Either one will work, so it really doesn't matter. And this is, you're going to write f of negative x. And if it comes out f of x, then it's even y-axis symmetry. If f of negative x equals then odd and symmetric across the order. Okay, so what I'd like you to do is work on the sample number 1 and sample number, not sample number 1, but if you go to your graphing packet that I handed out, I would like you to do number 1 and get through number 2 and get through as far as you can for Thursday, Friday. And there's going to be a couple more videos going over the other 2 scenarios where my degrees of my numerator and denominator are a little bit different, but we'll just kind of take it once at a time. So the first time I have 2 linears on top of each other, And the second time I have another 2 linear. So it's going to be the same way you find the horizontal asymptote for problem 1 and problem 2. Both of these don't look reducible, so you don't have that step on these. So you go straight to finding the zeros of the denominator and moving forward. Okay. I will see you on Thursday, or you can come on Wednesday between 10 and 12 and work on this too.